Here's a fun exploration that can be done with the Geometer Sketchpad software and with a programmable calculator. In this diagram, the angle denoted by the shaded sector corresponds to a number on the number line below the circle. To the left, you see the angle measured in degrees, followed by the angle as a fraction of a turn, or the angle over tau radians. So half a turn will correspond to the number 1/2, and a full turn corresponds to both 1 and 0, since it starts over again after a full turn. Now, in this experiment, I'm going to perform a rotation and dilation on a point. So I need to establish this angle as a rotation angle, and I need to construct a number to use as a scale factor for dilation. Let's set the scale factor to about 0.9 at first. We'll adjust it later by sliding this red dot on its segment. Now that I've established the angle and the scale factor, I will construct an arbitrary point to be rotated and dilated. Rotation of the point results in a second point, and dilation of the second point results in a third point. I'll hide the second point because it's an unimportant intermediate result. Now I demonstrate that wherever I put the first point, the second point is the transformed point is a fixed angle away from it. If I reduce the scale factor to 0, then I cause the transformed point to move to the center point. Changing the rotation angle also has the expected effect. Next, we try iterating this transformation. That is, whatever rotation and dilation was done to the first point, the same will be done to the second point to make a third point. And we'll iterate this 600 times. The points will spiral inward. Now, some interesting things happen when the angle is changed. The outermost point is moving slowly, but the inner points move faster. The closer they are to the center. Do you understand why? Now, because of the speed differential, the patterns change so that when you get to near an angle of 1/4 tau, the points appear to be 4 radial line segments rather than a single spiral. At half tau, there appear to be 2 line segments. At 2/3 tau, there are 3. At any rational number, the denominator of the reduced ratio will tell you the number of segments. But we won't recognize rational numbers with larger denominators unless the scale factor for dilation is increased closer to 1. Now, to make this even more beautiful, I'm going to glue my arbitrary point to a spot outside the circle so that the first transformed point is the fixed point on the circle. First, I reverse the 2 transformations by computing the opposite angle and the reciprocal scale factor. Then, with 2 transformations of the fixed point, I construct my target point. There's the fixed point. I rotate it. I dilate it. Lastly, I glue my arbitrary point to the target and hide the unnecessary points. I'll move the fixed point to the approximate right side of the circle. Now I'll animate the point that rotates about the circle to define the angle. Now watch carefully. The point on the circle is rotating so slowly that you can't see any movement, but the inner points are moving faster. Watch them and you'll see the magnified motion of the outermost point. If you increase the dilation ratio, you'll see this more clearly. As you gaze at this picture, you will be aware of the moments when the angle passes a rational number of low enough denominator to show radial lines. Three 35ths, 2 23rds, 3 34ths, 1 11th. Let's pause to make sure I'm really at exactly 1 11th. I'll count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this point here on the number line is at exactly 1 11th. Let's start it up again. 30 seconds, 2 21st. Let's pause again to count. Yep, it's 21. This point on the number line is 2 over 21. And this would be 1/10. One ninth. One eighth. One seventh. One sixth. Notice that whenever we get anywhere near a low denominator rational number, like say 1/5, you can see it coming from a long way off. There's 1/5. If you look in the middle, you see a sort of 5-sided figure. When I start it up again, just watch the middle. You'll see 1/5 appearing from the middle and working its way outward. There's 1/5. One fourth. One third. And almost the lowest denominator possible in a reduced fraction, 1/2. We'll go the rest of the way fast. By graphically depicting real numbers in this way, we can see when a number is rational or very close to a rational number. Now, following Vi Hart's series of 3 videos on spirals, Fibonacci, and being a plant, I'm going to use this picture to study rational approximations to irrational numbers so that I can get a clearer understanding of what it means for a number to be more irrational than another number. Let's start with the first irrational number ever discovered, square root of 2. If I want to find rational approximations to the square root of 2, I can use an algorithm like this. Set the denominator to 1, and then count up in the numerator until you get 2 big. We start with 1 over 1. We use a calculator to divide 1 into 1, and we get 1.0. This is our first rational approximation to the square root of 2, so we circle it. Next is 2 over 1. The calculator tells us it's 2.0. Not as close, so cross it off. It's also too big, which means we need to adjust the denominator. Next we have 2 over 2, which is 1.0, not better than our best approximation so far. And then we have 3 over 2, or 1.5, which is our new best approximation, but it's also too big, so we adjust the denominator again. Next we have 3 over 3, 4 over 3, which is 1.33. We can't compare this without computing another digit, so we use 1.333. We find 4/3 is the new best. Next 5/3, too big. 5/4, 6/4, 6/5, 7/5, which is the new best approximation. 8/5 is too big, so we continue on down the line. Well, I skipped 8/6 and 9/6 by accident, but that doesn't matter. The next winning approximation is 17/12. 17/12 is not going to be beat until 24/17. This algorithm may be tedious, but it is also simple and therefore easy to program a calculator to do automatically. For example, if you have a TI-83 or 84 calculator, you can enter programs such as this. Prompt for the value of p, the irrational number. Initialize some variables, numerator, denominator, the error, and then begin the loop part of the program. The first thing to do in the loop is check whether the latest rational number has a smaller error than e. If it does, then update the new best value for e and display the values of the numerator and denominator. The end statement is the end of the if block. The second thing to do is to decide whether the numerator or the denominator goes up by 1. The denominator increases only if n over d is greater than the irrational number p, otherwise the numerator increases. After those 2 tasks are done, loop back to the statement labeled A and continue forever. Actually, go-to statements are poor style in programming, so the program in my calculator looks slightly different from the program written here, although it does the same thing. Also, my display statement puts the 2 numbers on a single line separated by a period. There might be a way to do this with strings, but I didn't figure it out. Here's what happened when I ran the program on my calculator. You can see that I get the same rational approximations as when I ran through the algorithm on paper, but I go one step further to 41 over 29. Next, I tried it with another famous irrational number, pi, which you might know as half of tau. A funny thing happens after 22/7. There's a huge gap. 22/7 is, in some sense, an exceptional rational approximation to pi, because the denominator must get much bigger than 7 before 22/7 is improved upon. Even more exceptional, though, is 355 over 113. That is not improved upon even if I wait for hours. Let's get back to Geometer Sketchpad and see whether these characteristics of the square root of 2 and pi are evident. Here I've set my angle to square root of 2 times tau, as you can see in the value of p at the top left of the circle. My scale factor f starts out at 0 but grows toward 1 so that successive denominators of the rational approximations to square root of 2 become visible. If I pause here at f equals 0.9 there appear to be 5 spirals. I can set 5 as the denominator and trace through every fifth point to see whether that is correct. This corresponds to the rational approximation 7/5. Continuing a little way along, I can see another set of spirals. There are 12 of these, corresponding to 17/12. Continuing on, we still see the set of 12 spirals, but now we begin also to see spirals from 24/17. There's the 12 spirals, but we also see 17 spirals this way. 41/29 is also becoming evident. All of these different rational approximations can be seen in this view, but the spirals all look curved, indicating that they're all a little bit off. When I go out as far as my computer's precision will allow, I see evidence of the rational approximation 239 over 169. It's interesting that the denominator is a perfect square. I could try the next denominator, 408. The spirals do look like they are more in the radial direction, but I can't make a very good picture of it with this sketch. Now let's reset f to 0 and put in pi. Notice that right off the bat, the pattern looks like 7 radial lines. As f increases, the 7 spirals curve quite a bit, but we're still seeing 7 spirals. Till about 0.9995. And here, the next exceptional rational approximation to pi is found, 355 over 113. Now for the skeptical viewer, I'll show what happens when a number other than a nice denominator is put in. The spiral structure of pi reveals it to be what we might call less irrational than the square root of 2. It's closer to having the nature of a rational number, where the nature of a rational number is to have radial line segments instead of spirals. Here's a really clever trick that finds the rational approximations more efficiently. In fact, using this trick we can find the next exceptional approximation for pi beyond 355 over 113. We start with 1 and then count up until we exceed pi. Beep, beep, beep. There. This gives us 4, which exceeds pi. That's why it's written in red. This gives us our first rational approximation, which is either 3 or 4, whichever is closer to pi. The next step is to split 4 into 3 plus 1 and to rewrite 1 as 1 over 1. Then we count up this denominator until we no longer exceed pi. Beep, 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 beep. We've gone below pi again. Our next irrational approximation is either 3 plus 1/7 or 3 plus 1/8, whichever is closer to pi. Next, we split the 8 into 7 plus 1 and rewrite the 1 as 1 over 1. Then we count up the new denominator until we exceed pi. Beep, 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 beep. We choose the rational approximation closer to pi, and then we split the 16 into 15 plus 1. We write the 1 as 1 over 1, and count up. Beep. Oops, we've already gone under pi. This gives us the same rational approximation we had in the last step, and we move on, writing the 2 as 1 plus 1. Now this next step requires counting up quite high, so I'm going to use a binary search instead. Double, 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 double. Now I'm too high, so I go down by 128, down by 64, down by 32, up by 16, down by 8, down by 4, up by 2, down by 1. So it's between 292 and 293. And we could just barely tell from the last digit that 293 is the better choice. And so the next exceptional rational approximation to pi is, wait a minute, I have to do some arithmetic here. $104,348 over 33,215. And now we try the same thing on the square root of 2. Beep. 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 Is this pattern going to continue? Beep. Beep. This suggests an interesting conjecture. Maybe this pattern continues forever. Let's test it. This kind of expression is called an infinite continued fraction. It might be better written this way. Actually, there's another notation that looks similar to this but uses horizontal fraction bars and no parentheses. Now notice the pattern is broken only at the start. Actually, we should look at the square root of 2 plus 1 because then the pattern would be nice all the way through. So let's write our conjecture in terms of the square root of 2 plus 1. Our conjecture is square root of 2 plus 1 is 2 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over and on forever. If the number on the left side is called x, then the right side must also be equal to x. But then, by the symmetry of the expression, a subset of the right side is also equal to x. And this leads us to an ordinary algebra equation. In fact, it is not only ordinary, it is a quadratic equation. So let's solve it to see whether square root of 2 plus 1 is a solution. Ha! It is! But what about the other solution? How do we know that the continued fraction is not equal to the other solution? Well, remember that the continued fraction is an infinite expression, and infinity is always a shorthand notion for some limiting process. But the limiting process in this case does not lead to 1 minus the square root of 2, but clearly it leads to 1 plus the square root of 2. Now we can investigate the square root of 3 by the same method, and again a pattern is seen. 1, 2, 1, 2, 1. Also, again, the square root of 3 plus 1 is prettier. Using the same method to turn this recursive formula into a quadratic equation, we again find an equation with a solution set including the square root of 3 plus 1. Now this suggests an idea for constructing a number that might be thought of as the most irrational number possible. If the pattern is full of ones, then there will be no exceptional rational approximations. There will always be a slightly higher denominator that gives a slightly better rational approximation. The number that we seek turns out to be the famous number phi, the golden ratio. Phi has the property that phi plus 1 is to phi, as phi is to 1. So if you have a 1 by phi rectangle and you attach a phi by phi square to it, then you get a new rectangle that has the same ratio. Okay, it's phi on this side, and then 1 plus phi on that side, so it has the same ratio. Now if we run our calculator program again and put phi in it, a very exciting result is seen. Okay, 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8, 21. These are the numbers in the Fibonacci sequence. And if you think about it, since the reciprocal of phi is phi minus 1, then the denominators of the rational approximations for the reciprocal of phi must be the same as the denominators for the rational approximations for phi. And you could predict that the set of numerators must be identical to the set of denominators. Now let's go back to Geometer Sketchpad and put in phi, and we'll see the sort of patterns that are made by sunflowers and many other types of vegetation. Now let's go back and look for the numbers of the Fibonacci sequence. Okay, right away it looks like 3 points, but not for long. Here we have 5 and 8. If we run it further, we see 8 and 13. Continuing on, we see 13 and 21. 21 and 34 is next. Different Fibonacci numbers are apparent at different densities of points. But you won't ever see the sunflower seeds form a straight radial line. They will always form spiral curves. I'll end with just some pictures of the spiral paths. Again, if you're interested in why plants grow this way, take a look at Vi Hart's 3-part video series on spirals, Fibonacci, and being a plant. Also, if you want to know more about the continued fraction representation of radicals and what precisely is meant by calling a rational approximation exceptional, then you should look into number theory and Hurwitz's theorem and convergence.